Hello, everyone, and welcome to Lecture 7, Periodic Trends. In this lecture, we're going to look at 4 different periodic trends: atomic radius, ionization energy, electron affinity, and then we're going to wrap up with electronegativity. You can see that there's a trend on the periodic table associated with atomic radius, and that trend increases from top to bottom of a group column or family, and also from right to left on the periodic table, with the largest atomic radius being down here in the southwest corner of the periodic table. When we look at some data associated with atomic radius, we can see that all of those alkali metals like lithium, sodium, potassium, rubidium, cesium, they all have the largest atomic radius. And they're all on the left side of the periodic table. So the trend that we just looked at is demonstrated by this data, where measurements in picometers of atomic radius were taken. When we think about the increase from the top to the bottom of the periodic table, and so you can see that cesium here has the largest atomic radius, demonstrating that in the alkali metals, if we look at lithium, sodium, potassium, rubidium, and cesium, and also francium over here, demonstrating that the alkali metals on the periodic table are increasing in atomic radius in that group column or family from the top to the bottom of the periodic table. And just having looked at quantum mechanics and electron configurations and orbital diagrams, we know why this is the case. We said before when we first started this class that electrons are responsible for atomic volume. And that's because those electrons are in the electron cloud. Remember, we said that the protons and the neutrons are in the nucleus, responsible for the mass of the atom, because their mass is some 200-fold greater than that of an electron. But we know that the electrons are in the electron cloud, housed in the orbitals. And we know that as we increase the shell number, we increase the distance of the electrons housed in those shells from the nucleus. So the further we get with the electrons away from the nucleus, of course, that's going to correspond to a greater atomic radius. And as we go from the top of the periodic table to the bottom of the periodic table, that's exactly what we're doing. We're increasing the shell number from 1 to 7, and we're increasing the energy that's associated with those electrons because they are further away from the nucleus, thereby increasing the atomic radius. Now, the other question is, why would the atomic radius increase on the periodic table across a period or row from the right to the left? Or we could similarly say that the atomic radius decreases as we go from left to right. Well, think about what's happening as we go from left to right across the periodic table. We're increasing the atomic number as we go from left to right across a row or period. And as we increase the atomic number, we are adding 1 electron and 1 proton with every increase of 1 in the atomic number. That means that we're adding a positive charge and a negative charge. That positive charge and that negative charge are going to have a force associated with them, and that force is attraction. And it's because of that force that every time we add another proton and another electron, as we go from left to right across a row or period, the atomic radius is contracted and thereby decreases every time we add that additional force. Now, looking at that force associated with the quantum mechanical model, and we said that in quantum mechanics, we could have electrons residing at specific energy levels. The electrons you can see here with this particular diagram are repelling one another between those energy levels. So the red arrows are showing repulsive forces between electrons, and these little blue spheres are denoting electrons. And so we have these repulsive forces between all the electrons, essentially holding those electrons at a specific position. In addition, we have these blue arrows that are showing attractive forces to the nucleus. And remember, the nucleus has positive charge associated with it. So these blue arrows are showing attractive forces between the electrons and the positively charged nucleus, while we have repulsive forces going on between like-charged negative electrons. And all of those forces together are holding those electrons in certain energy levels that are allowable. Looking at the periodic trend again in atomic radius, we can see these increases from top to bottom, which are associated with the shell number. So we're putting electrons in increasingly larger distances from the nucleus, and each shell then is further away, it has the electrons further away from the nucleus, and that gives us a larger and larger atomic radius. As we said, going across the periodic table from the left to the right, we're going to see a decrease in the atomic radius because we see an increase in the atomic number, which gives us an increase in protons and electrons, and their attractive forces contract the size of the atom, and therefore the volume and the atomic radius decreases. So let's look at a question: which of the following has an atomic radius that's smaller than sulfur? And if we use the knowledge that we have, then we can use the periodic trend to make a determination about this. So oxygen is directly above sulfur, and we know that the atomic radius increases from top of the periodic table to the bottom of the periodic table. So oxygen is clearly got a smaller atomic radius compared to sulfur. If we look at chlorine, chlorine is just to the right of sulfur, and we know in the trend of atomic radius, it's decreasing from left to right. So that means chlorine with an atomic number that is 1 higher than sulfur, sulfur at atomic number 16, chlorine at atomic number 17, that means that chlorine has 1 more proton and 1 more electron, and that attractive force is contracting the size of the atomic radius. And so chlorine is also smaller. Which one is substantially smaller than sulfur? Well, oxygen is clearly smaller relative to sulfur than chlorine is, but they're both still smaller than sulfur. Calcium, on the other hand, is an alkaline earth metal, all the way over on the left side of the periodic table, and we know that atomic radius increases from right to left, so we know that calcium is going to be larger than sulfur. And lithium is an alkali metal, even further to the left on the periodic table. So we know that relative to sulfur, lithium is going to be larger. So this question could be answered by either A or B. A is the best possible answer because clearly if we're just looking at the trend and we're not looking at quantitative values, then oxygen is clearly the smallest. But the answer would be A and B, even though the answer here on this slide is saying it's just A. When we look at the trend in atomic radius based on cations and anions and formation of an ion, the cation of an atom decreases in size, while the anion of an atom increases in size. And the trend cannot be made according to the periodic table, but by isoelectronic series. And so let's talk about what we mean by isoelectronic series and making a determination about the atomic radius of an ion. If we look, for example, at a couple of different species, we look at a sodium atom and we look at a sodium ion, and we ask the question, which one is smaller? Let's start with the sodium atom, and we look for the atomic number of sodium. It's 11. So we know that we have 11 protons, and we also have 11 electrons for an atom of sodium, which is neutral. Now let's think about what happens with sodium when it forms an ion. And we have electron configurations and orbital diagrams that we can look at now. So we could draw the Aufbau principle and write out the electron configuration, or we can use the periodic table if you have a periodic table in front of you. And so that would be 1s2, 2s2, 2p6, and remember we have 11 electrons to take care of here, and right now we have 10. And so we would go from 2p6 to 3s1. And if we draw the electron configuration and orbital diagrams, so I'm going to do the orbital diagram in red. There's our 1s orbital, our 2s orbital. Here's our 3, 2p orbitals, and then our 3s orbital. And we have 2 electrons in both the 1s and the 2s subshells. And we have 6 electrons in 2p. We put 1 in each orbital, and then we backfill and pair. And then 1 in 3s. Okay, if we form a sodium ion, this species is going to want to have a perfect octet. So it's forming an ion in order to have the electron configuration of neon, the noble gas that's closest to it. In order to have the electron configuration of neon, then sodium would have to give up one of its electrons. Which electron is it going to give up? It's going to give up this one in the outermost, or the third shell, because that's furthest from the nucleus, and it will be the most energetically favorable to give up. When that happens, then sodium in its second shell, because this is 2s and this is 2p, this was 3s. So in its second shell, it now has a perfect octet, 8 electrons. So when we look at the ion of sodium, it now has 11 protons here and 10 electrons out here. It has a lot more positive charge than negative charge, considering that it has an extra proton relative to the number of electrons. And it's lost that other electron in the 3 shell, in the third shell, or the third energy level. So where you used to have an atomic radius that was this big, you now have an atomic radius that is decreased because n equals 3 is now gone. N equals 2 is now the outer shell. So the atomic radius is going to be smaller for the sodium ion. And here's a little better artist sketch than the one that I just drew, but you can clearly see that when we're talking about a higher positive charge in the nucleus relative to the negative charge in the electron cloud, those positive charges are going to have more strength and force in drawing those electrons in towards the nucleus, and that decreases the size of the sodium ion. In addition to, we don't have electrons in shell 3 anymore. Our outer shell is now shell 2. So here's another your turn associated with chlorine, and I'm going to leave this one for you to do. There is a solution, so if you get lost when you're looking at this, evaluating this, then you have a solution that you can fall back on. But ultimately, you need to be doing the explanations without the solution in front of you. So let's look at this one. Compared to oxygen, nitrogen has a larger atomic radius. Is this true or false? And we look at the periodic table and we say nitrogen has atomic number 7. Oxygen has atomic number 8. So therefore, oxygen with 8 protons and 8 electrons, nitrogen with 7 protons and 7 electrons, there's going to be a greater attractive force associated with the oxygen. And it will, of course, be smaller than the nitrogen is. So the statement is true. And we've been talking about these electron configurations and orbital diagrams and how all of these species on the periodic table are going to gain an oxidation state so that they can have the electron configuration of the Nobel gas that's closest to them. So let's have a look at the atomic radius, or the impact on the atomic radius when these species form these ions from their oxidation states. If we had, for example, and we've talked about this before, that hydrogen can either have a positive charge or a negative charge, which is why it kind of floats around on the periodic table, because it can act like a metal and get a positive oxidation state, or it can act like a non-metal and get a negative oxidation state. When hydrogen gets a positive oxidation state, that means it's given up its one and only one electron, and the only thing left is the proton in the nucleus. And you notice that when that happens, we have no electron configuration for a Nobel gas that's associated with no electron. But if hydrogen gets a negative oxidation state, that means that hydrogen now has 2 electrons. With 2 electrons, hydrogen has the electron configuration of the Nobel gas helium. So in other words, hydrogen started out at 1s1. But when hydrogen gained 1 electron and became H-, we now have an electron configuration that is 1s2. And that is the electron configuration for the Nobel gas helium. We can go through any of these oxidation states, and you should go through most all of them. I'm going to focus on these oxidation states here because there's a variation associated with them. You can see the asterisk. And the asterisk has a note at the bottom of this data table that says these ions do not have a true Nobel gas electron configuration because they have an additional filled D subshell. Well, let's first look at aluminum. So if we look at aluminum and we do the shorthand electron configuration, aluminum's shorthand electron configuration, I'm not going to erase them now, it's going to be neon. And then if we use the periodic table or the Aufbau principle, it doesn't matter which one you want to use, we have 3s2 and then 3p1. To get to aluminum. And now let's think about what would happen if we had aluminum 3+. We would have to lose 3 electrons. And so we're going to give up this outermost in the p orbitals, and then we're going to give up this outermost 2 electrons in the s orbitals. That's going to give us the 3+, and what you notice is the only thing left is the core electron configuration for neon. All right, let's look at one of the other 3 that are there. Let's just take a look at gallium, for instance. And we also have indium and thorium. They're going to act exactly the same as gallium will. So when we look at gallium, again, we have neon. I'm sorry, wrong. We have argon. Let me erase that. So we back up to the closest Nobel gas, and that would be argon with an atomic number of 18. Gallium has atomic number 31. So we write argon, and then we have 4s2. And then we have 3d10. And then we have 4p1. Okay, when we examine this electron configuration, we can see that our highest shell number, that is the shell that's furthest from the nucleus, is shell 4, or energy level 4. So we're going to be removing electrons from the outer shell first because they're the easiest to remove, because they're furthest from the positively charged nucleus. So that means they have the least amount of attractive forces, and therefore they're the least stable and the most energetic to remove. So we remove this one electron in 4p. We remove these 2 electrons in 4s. And what we're left with here is not just argon's electron configuration. We're left with argon's electron configuration, but we're also left with a filled 3d orbital. So we don't exactly have just argon's electron configuration, and therefore we don't have, with the oxidation state of these 3 species that have an asterisk, the Nobel gas electron configuration when they become oxidized. So these are exceptions, and of course, as I always say, those exceptions are probably going to find their way to the exam, so this is not something that you should overlook. And you should go through the rest of this table, or a good majority of this table, draw out the electron configurations, and have a look at how, in obtaining those oxidation states, these species gain the electron configuration of the Nobel gas that's closest to them, and therefore their radius is going to be the same. And so when we look at these gallium, indium, and thorium that have an asterisk by them, they won't have the same radius as neon or argon or krypton, but certainly aluminum, O2 minus, F minus, magnesium, and sodium are all going to have the same atomic radius as neon. And if we look at lithium +1, it's going to have the same atomic radius as helium. Hydrogen -1 is going to have the same atomic radius as helium. And you can look at these others, draw out the electron configurations, and prove to yourself that as these species gain an oxidation state that gives them the electron configuration of the Nobel gas closest to them, they also have the same atomic radius as that Nobel gas. Ionization energy is the next periodic trend we're going to evaluate. And ionization energy is defined as the amount of energy it takes to remove the outermost electron from an isolated neutral atom in the gaseous state. It's abbreviated often, not always, but often, with this uppercase E and the subscript I. You'll see ionization energy abbreviated a few other ways. Don't get too bogged down about the gaseous state and the neutral atom. The reason that we're talking about removing an electron from a neutral atom is because we're talking about the first ionization energy. We can also remove an electron from a charged species, an ion. We do this in successive ionizations, and we'll talk about that. We talk about gaseous state atoms because it's easier to work with removing electrons from a gaseous state or adding electrons to a gaseous state atom. Turns out that if we remove that one electron from hydrogen, it's going to cost us 1,312 kilojoules per mole. And you'll notice that the units for ionization energy are given in kilojoules per mole. They can be given in other ways, in kcals per mole or in joules per mole, but often when we look up these values on tables, data tables, we see the units in kilojoules per mole. So this is the most popular convention. So talking about ionization energy, it increases from left to right across the periodic table and bottom to top on the periodic table. So it's going to be this northeast corner that's going to have the highest ionization energies associated with them. And if you think about this, well, we have fluorine up here, in this northeast corner. And fluorine and chlorine and bromine, all of these species over here on the left side of the periodic table have one thing in mind in order to become stable and get the electron configuration in the Nobel gas that's closest to them, and that is to gain electrons. Over on the other side of the periodic table, to get to the Nobel gas that's closest to them, these species over here have one thing in mind, and that is to lose electrons. So you can see why the highest ionization energy, if you have a species that wants to gain an electron pretty badly, then it's not going to want to give an electron up. And that's what ionization energy is about. It's about stripping electrons away. So those species that are over either at the top of the periodic table or over on the right side of the periodic table are not going to be interested at all in giving up an electron. And let's think about writing some electron configurations and see why that is the case. And if we write the electron configuration for fluorine, then fluorine has the core of helium, which doesn't save us a lot, but it's shorthand, it saves us a little. And then after that, we have 2s2. And then to get to fluorine, we have 2p5. So that gives us a total of 2, 4 plus 5 is 9 electrons, and fluorine has atomic number 9. So it has 9 protons and 9 electrons, so we've accounted for all of them. Now if we draw the orbital diagram, and we'll just draw the orbital diagram for the outermost electrons. So we'll draw this is the 2s, this is the 2p, and I'll get a different color so there's a little bit of contrast. 1, 2, 3, and then 4 and 5. So for fluorine, the only issue here is that fluorine wants to put an electron right here. If fluorine puts an electron right there, then fluorine would have a perfect octet, and it would be stable. So fluorine definitely does not want to give up any electrons it has. It wants to, in fact, gain 1 electron. So we're looking at fluorine saying it's going to have a lower ionization energy relative to the fact that it wants to gain this electron. It's still high, so let's not think about it. It still has a very high ionization energy. When I say lower, I mean relative to another species here. And that species is helium, because helium, as you know, is a noble gas. And so helium has a very stable duet. So with helium having a very stable duet, being a noble gas, we know that even though fluorine is a very high ionization energy, it's lower relative to helium. Now let's have a look at nitrogen. Nitrogen is to the left of fluorine. And so if we use the trend now, the ionization trend, we know that nitrogen will have a lower ionization energy relative to fluorine. And since fluorine is lower than helium, then nitrogen's ionization energy would be lower than both of them. Sulfur drops down 1 on the periodic table in row 3, and we have fluorine in row 2. So we know if we're talking about shells that sulfur would have a lower ionization energy relative to either nitrogen or fluorine, and that would make it relatively lower than helium. So it really has a lower ionization energy than A, B, or C, helium, fluorine, or nitrogen. And so clearly our answer to this question is helium. Now, could you have answered it much more quickly than that by just saying helium's a Nobel gas, it has a duet, it's stable? Of course you could have answered it more quickly than we did. But the issue is, this isn't the only question you're ever going to be facing. And so I went through this sort of process of elimination to demonstrate for you what kind of a method you're going to use when you have a question like this to resolve it. And we used a combination of things. We used electron configurations and orbital diagrams from quantum mechanics, and we also used the trend on the periodic table that states ionization energy increases from left to right and bottom to top. So you can see that ionization energy not only has a trend that's qualitative, that is, increases on the periodic table from left to right and bottom to top, but you also see a quantitative trend. So when we look at the Nobel gases over here, you can see that their ionization energies are very, very high relative to any other species on the periodic table. And again, that's because they have a stable octet, or helium with 2 electrons has a stable duet. But you can also see this increase from left to right. So look at lithium with an ionization of 520 kilojoules per mole versus fluorine, 1681 kilojoules per mole. And we can also look bottom to top, 926 to 1681. And we can look in any column we want. There are going to be a couple of glitches associated with ionization energy. And we'll talk about what those glitches are and how we evaluate them based on what we know about quantum mechanics. Now let's talk about successive ionization energy, and that ties into looking at the glitches that are associated with ionization energy being higher or lower for some species on the table that we just looked at. Again, I'm not going to ask you to memorize any of that data on that table we just looked at, but I may be asking you to explain some glitches that are associated with an ionization energy on the periodic table that we expect by the trend to increase, but it decreases. So if we start with magnesium atom, you can see that magnesium atom has an atomic radius this size. If we go to Mg plus over here to the right, we see this decreased atomic radius. And if we go down here to Mg2 plus, we see even more decrease in the atomic radius. And we can explain this using quantum mechanics, electron configurations, and orbital diagrams. So for magnesium, the electron configuration is given here. On a test question, I definitely wouldn't be giving you this. You'd need to derive it. But you can see that we have 2 electrons in shell 3. Now, to go from magnesium to magnesium plus 1, we're going to give up one of those 2 electrons. And so we end up with a 1 here, and that's exactly what you see over on this side. You're seeing 3s1. Giving up that 1 electron means that we have more protons relative to our number of electrons. In fact, we have 12 protons and 12 electrons here. Over here we have 12 protons and we have 11 electrons. And so there's more positive charge than negative charge pulling in on those electrons and contracting that atomic radius so that it's smaller. Notice that to remove that first electron, the ionization energy down here in this table is 738 kilojoules per mole. And think about this. We now, in the outer shell, only have one electron with Mg+. So to remove that one electron, but remember, we have a stronger pull from the nucleus. So to remove that one electron, it's going to cost us twice as much as removing the first one. It's going to cost us 1,451 kilojoules per mole. And again, that makes sense because we have more positive charge in the nucleus holding less electrons in the electron cloud. And so they're pulling them in. The positive charges are pulling on those electrons much more strongly with an attractive force. Now let's evaluate Mg2+. And just looking at the table of data, you can see that to take that third electron is going to cost us 7,733 kilojoules per mole. That's not 2 times. So this one was 2 times more energy. That's more like 5 times plus more energy to get that third electron. And so when we think about what's going on here and we look at this electron configuration, we see that the 2s, so the second shell, has a perfect octet. There are 8 electrons in the outer shell now. And so that is very, very stable. 8 electrons in the outer shell. We now have the electron configuration of neon. We also have the atomic radius of neon. And it's going to be very, very difficult to remove an electron from a species that has the electron configuration of a Nobel gas and is now very stable. The next trend we're going to talk about is electron affinity, and this is adding an electron to an atom in the gaseous state. And so if you think about the periodic trends that you know about, well, what species on the periodic table are interested in adding an electron? And that would be those that are on the left side. So again, this is going to be a trend that's going to increase from left to right and bottom to top as we evaluate it. And the one thing that I want to explain to you is that electron affinity are generally negative values because the energy is being released. And students often get confused about this because I said that we have an increase in electron affinity from left to right and bottom to top. That means that the highest magnitude of numbers are going to be seen up here in the northeast corner again. We're not talking about that all of these numbers, remember, have negative signs in front of them. We're not talking about a number scale. So a number scale would have 0, -1, -2, -3, and so on. And then over here, you would have +1, +2, +3, and so on. And if you're talking about a number scale, then you're going to say, okay, so that means these numbers are larger and these numbers are smaller. But with electron affinity and chemistry in general, when we put a negative sign in front of a value, that doesn't mean that it's smaller on a number scale. We're in fact not using a number scale when we talk about negative numbers from this aspect. We're talking about exothermic reaction. Exothermic means energy is being released. That's what exothermic means. We can have an endothermic reaction. In an endothermic reaction, energy is absorbed. So if we had, for example, an exothermic reaction that was associated with 785 kilojoules per mole of energy versus an endothermic reaction, which is associated with 785 kilojoules per mole of energy, the magnitude of both of these reactions is exactly the same. The magnitude regardless of where you're looking at the exothermic reaction, which has a negative sign in front of it, or the endothermic reaction, which has a positive sign in front of it, you still have 785 kilojoules per mole of energy. In one case, that 785 kilojoules per mole of energy is being released. In the other case, that 785 kilojoules per mole of energy is being absorbed. But one of those values is not smaller relative to the other one, because again, we're not looking at this from a number scale aspect. We're looking at this from a magnitude of energy aspect. Going back to what you know about the periodic table, you know that alkali metals, alkaline earth metals, and transitional metals all want to give up electrons so that they can get the electron configuration of the noble gas that's closest to them. On the other hand, nonmetals like halogens, chalcogens, they want to accept electrons to get the electron configuration of the noble gas that's closest to them. And then metalloids may either give up or accept an electron depending upon their characteristics. So clearly, this shows us that we're going to be increasing in electron affinity values from the left to the right and from the bottom to the top, because those are the species that want to gain an electron. And it would be most favorable. So they're going to release the highest amount of energy when they get an electron. We can look at this data for electron affinity, and we see that we have fluorine and chlorine and bromine and iodine, and that is clearly what we would think, because they all want to gain an electron to get the noble gas configuration that's very close to them right next door. So they want that electron pretty badly, because one and only one electron makes them stable. So they'd have a very favorable electron affinity, which would be a high magnitude with a negative sign in front of it, because you would release a lot of energy in that favorable reaction. Fluorine, you notice, we would think should be the highest, but it's not quite. It's a little bit lower than chlorine. And the reason for that is that fluorine has such a small atomic radius that those electrons that it holds and the protons that it holds are drawn into a very small region, because they're in the smallest region, that is, their shell number is 2. To pack another electron in with the electrons that are already there in that small region is a little bit more difficult than it is with chlorine, chlorine being in shell 3, or bromine for that matter in shell 4. But clearly you can see at the bottom we have all the noble gases, which again is not surprising, having noble gases at the very bottom with these energy electron affinities that are associated with 0. Not surprising at all. And then if we look at some of our other species like beryllium or calcium or magnesium, it's not surprising again, or transition metals, because they don't want to gain an electron. They actually want to give electrons up. So let's look at fluorine, phosphorus, sulfur, and boron, and let's think about the trend on the periodic table to resolve this question. And we know that fluorine has a very high electron affinity. In fact, it's higher than, we don't have any other halogens listed here, so fluorine is going to be higher. They're asking us to put these in order of increasing electron affinity, and so we know that fluorine is going to be the highest. And so then we need to think about phosphorus, sulfur, and boron. And phosphorus and sulfur, atomic number 15 and atomic number 16, are side by side, and they're closer than boron. They're only one row below boron, but they're much closer than boron to the right side of the periodic table. Sulfur being the closest, and then phosphorus. And so that leaves boron with the lowest electron affinity. This table is just showing you some values, some actual values for electron affinity. And again, we're looking at the noble gases, and we see that noble gases don't want, nor do they need, an electron to be stable. And so the electron affinities there are all 0. When we look at chlorine, we can see that trend that we talked about with the data we just looked at, where chlorine has a little bit higher magnitude of electron affinity than fluorine. Chlorine has 349 versus fluorine with 328. But the overall trend, as you can see, is increasing from the bottom to the top of the periodic table, and also increasing overall as we go from the left to the right. There are a few little glitches, and again, the way you explain those is to look at the electron configurations in the orbital diagrams and see where that species is most stable. And that will help you explain glitches that you see. So here's a summary of atomic radius, which is the red arrows, which increases from top to bottom and right to left. The other two trends that we've looked at, ionization energy and electron affinity, both increase from left to right and bottom to top of the periodic table. And the way that you should remember these sorts of things is to keep in mind that fluorine is right here in group column or family 7A. Fluorine is at the top northeast corner and has the highest ionization energy and the highest electron affinity. The highest ionization energy because it's going to cost a lot to take an electron away from fluorine. The highest electron affinity because that's a favorable release of energy, and fluorine's happy to gain an electron. The last trend we're going to cover is electronegativity. Electronegativity is a measure of the relative attraction that an atom has for shared electrons in a bond. So now we've gone from talking about an isolated atom to atoms that are sharing electrons in a bond. The species with the higher electronegativity has a greater attraction for electrons and negative charge. And if we look at the word electronegativity, we see electron here and we see negative charge here. So those species that have a high electronegativity want electrons. They want negative charge. And we assign numerical values because this is quantitative. So fluorine is the most electronegative on the periodic table, has an electronegativity value of 4, a relative value of 4. That means that, again, we have a trend that's going to increase from left to right and bottom to top because fluorine is in that top northeast corner of the periodic table. Now, we've already discussed these points up here, just discussed them, but I want to talk about an ionic bond. And so remember that in an ionic bond, metals lose electrons, and so they have a very low electronegativity. They give up electrons to get the electron configuration of the noble gas that's closest by. Nonmetals gain electrons. They gain electrons to get the electron configuration of the noble gas that's closest by. And so nonmetals are going to have a high electronegativity, while metals are going to have a low electronegativity. And this slide is just showing you that increase of electronegativity from left to right and bottom to top, which again makes sense because species over here like fluorine or oxygen that are very, very close to the noble gas neon are going to want to gain electrons so that they can get that electron configuration. But if we look over on the other side of the periodic table, species like lithium or sodium or magnesium or beryllium, they are all going to want to give electrons up so that they can get the electron configuration of the noble gas that's closest to them. And so they don't want electrons. They don't want negative charge. They want to get rid of those electrons. They want to get rid of that negative charge. And therefore, they're going to have very low electronegativities, very high electronegativities over on this side. So which of the following has the highest electronegativity? And if we use the periodic table to evaluate this trend, we know that sodium is on the far left. That's going to be associated with a low. Not only is it on the far left, but it's close to the top of the periodic table, but that's going to be associated with low because it wants to give up electrons so that it can get the electron configuration of neon. Neon, of course, that's a 0. Neon has no desire to gain electrons. It's stable the way it is. Fluorine has a huge desire to gain just 1 electron. And so it has a very large electronegativity because if it just gets that 1 electron, then it has the electron configuration of the noble gas that's very close to it. Selenium, of course, if we look for selenium on the periodic table, then we can see that selenium is in the same group column or family with oxygen, has atomic number 34 if you're searching for it. So the same group column or family with oxygen, but it is below fluorine, substantially below fluorine, a couple of rows, a couple of shell numbers below fluorine. And so because it is lower on the periodic table, and I'm just going to write PT, compared to fluorine, then it's going to have a lower electronegativity compared to fluorine. Now again, could you have answered this question fairly quickly? Well, I'm sure you could, because you know that fluorine has the highest electronegativity on the periodic table. That's already probably stuck in your memory bank. But you probably won't get a question that's this direct and easy on the exam, and so you're going to have to use either the periodic trend or quantum mechanics to make some decisions here. When we talk about electronegativity, again, we're not talking about an isolated atom in the gaseous state. We're talking about 2 atoms that are involved in a bonding interaction. And so this is what brings in polar covalent bonds versus nonpolar covalent bonds. And they're associated with these fractional charges. And so if we evaluate something like water, for example, and we can do that by using another model that we learned, and that is Lewis structures. So we draw the Lewis structure of water, and we start to evaluate the electronegativity associated with each atom on either side of this bond. So I'm going to look at the hydrogen and the oxygen on the left side, and then I'm going to look at the bond of the oxygen and the hydrogen on the right side. And of course, they're chemically equivalent. So whatever I learn about one bond, the bond on the left, that will be the same as the information associated with the bond on the right in terms of chemistry. The oxygen is more electronegative. I can see that from the trend on the periodic table. Hydrogen is off to the left. The oxygen is over on the right side. And so we designate that additional electronegativity associated with that oxygen with a delta symbol and a minus sign by it. Now that delta symbol is a fractional charge. That is not a full -1. The delta means it's a fraction of 1, which means this: oxygen is withdrawing these 2 electrons very close. It's withdrawing these 2 electrons away from hydrogen and getting them very close to its own nucleus. Okay. The same thing would happen over here. Oxygen would withdraw these 2 electrons in the bond very close to it, and they would be fairly far away from the hydrogen. That means that the hydrogen is going to have a partial or a fractional positive charge, each one of them, and we designate that with a delta plus. We can also show this bond polarity, what we call bond polarity, and so these bonds are both polar. We can show that bond polarity by drawing an arrow with an arrowhead that points towards oxygen and a positive symbol on the other tail end of it that points towards our least electronegative atom. And we can do that on this side as well. So electrons are dominantly located in regions that are close to the atom that has the higher electronegativity, and that gives it the partial negative charge. And so that extra electron that's being still shared with hydrogen is closer to the oxygen nucleus. And here are some more bond polarities that are drawn out for you. Let's take a look at some of them. And again, the delta plus represents the partial positive charge. The delta minus represents the partial negative charge. Looking at the periodic table, let's look at this one, calcium fluoride. Calcium is all the way over on the left side of the periodic table. Fluorine is all the way over on the right side of the periodic table. And so just using the trend, we can see that calcium has the delta plus and fluorine has the delta minus. And then we can also draw the arrow showing this, which they've done right below. Lithium bromide, again, bromine all the way on the right side of the periodic table, lithium all the way on the left side of the periodic table. So lithium is not very electronegative. It does not want negative charge or electrons associated with it. It wants to give them up. So it's going to have a partial positive charge while bromine has a partial negative charge. Where are the electrons going to be in this bond? Very, very close to the bromine. Not close to the lithium. Similarly, in this bond, very, very close to the fluorine nucleus and very, very close to the chlorine nucleus, pulling them away from the hydrogen substantially. So again, electronegativity is talking about the atoms on either side of a bond, and we're looking at those atoms on either side of the bond to determine which is more or less electronegative using the trend on the periodic table, or alternatively, electron configurations and orbital diagrams if things get too complicated, to make a determination about which species is going to want the negative charge or the electrons more compared to another to get the electron configuration of the Nobel gas closest to it. This slide I'm not going to cover right now. I'm going to save it for later because it has a lot to do with valence shell electron pair reaction theory, which we're going to cover probably this upcoming week. So that wraps up our lecture 7 for periodic trends.